Hi, my name is Bill. Welcome to Probability and Statistics for Everyone. This is video 4. Well, it's part of video 4. In the previous videos, I pledged to you that here in video 4, we'd look at various ways of presenting, describing, and summarizing data, and we are going to do that. But I find now that I'd prefer to break that topic up into smaller, more manageable pieces. So we'll call this video 4.1 and focus here on dot plots and empirical distribution functions. So let's get started. As I said, in this video we're going to focus on two ways of presenting data graphically, because graphical displays have the potential to instantly reveal something to the eye that hard numbers simply can't convey to many of us. We'll begin by considering these 10 values, which I'm presenting to you as random samples from some system or process. The first thing we'll do with these values is present them in what's called a dot plot. As you can see, a dot is placed along the x-axis for each value in the data set. To illustrate this explicitly, the lowest and second lowest values are pointed out in the data and on the plot. This kind of plot is most useful when the number of data points isn't too large, because when there is a large number of points, they tend to overlap on each other and form horizontal blobs. And blobs aren't good. What blobs can indicate is that there's a group of values near some point, but any detail about where the dots are within the blob is lost in the overlap. In this plot, we don't see a blob, but we see a grouping of values near x equals 4. The next plot that I want to present to you is an empirical cumulative distribution function, generally just referred to as an empirical distribution function, or EDF. The EDF is a mathematical function along the entire x-axis that displays the fraction of the sample points that are less than or equal to any value x. For example, if we look at the dot plot, we can say that the number of samples that are less than or equal to 1 is 0, because the lowest value in the measured data isn't until 1.24. On the other hand, there is 1 point less than or equal to 2, and with a total of 10 data points, the fraction of sample points less than or equal to 2 is 1/10. So let's look at the EDF for this data set, drawn slowly. As I said, the EDF is a function defined over the entire x-axis, but we'll begin to build our EDF by starting at the origin, x equals 0. As we were just discussing, we see the EDF jump to 1/10 at x equals 1.24, and jump to 2/10 at x equals 2.47, and so on. Eventually, if we're patient, the full EDF is drawn. Notice that with only 10 data points, this EDF appears rather jagged with its 10 jumps of 1/10 each. Also notice that around x equals 4, where there is that close grouping of dots on the dot plot, there is a perceived steep climb upward on the EDF because of the closeness of those dots. We'll explore what these two kinds of plots can reveal about the underlying data when we have more specific sets to investigate. Here I wanted to focus on the mechanics of generating the plots, but I want to make a comment before we proceed. I'll repeat it later in this video or in other videos, but I believe it's important enough to go ahead and say now. Both of these plots present the data in its entirety. There's no averaging or rounding or binning or any other transformation of the data. As already acknowledged, the dot plot can blob things up, smear them together if there's too many of them overlaid on each other, but all of the data is there. Now, I'll clarify that a little bit more as we proceed, but I wanted to lay that marker down now. That is why these are my first go-to plots whenever I receive a new set of data. Now that we've done that, we'll need to take a brief mathematical detour. Anyone with even a moderate level of training in mathematics will object to this EDF plot, or my characterization of it as representing a mathematical function, or both. That's because a proper mathematical function will define one and only one value of y for each value of x. And each vertical line on this EDF is a violation of that. Even though this EDF, as shown, is the common way of presenting the EDF, the mathematically proper way of presenting it would look more like this. On the right-hand side of each horizontal line, except the last one in the upper right-hand corner, is an open circle. That is indicating that the value of that line, 0 or 0.1 or 0.2, etc., is true right up to that point, but not including that point or that value of x. For example, the jump to 1/10 occurs right at 1.24, but not less than 1.24. So that 0 line goes all the way up to not even 1.23999999, let the 9s go out forever. That still has 0 points to the left of it. That jump doesn't occur till 1.24. For that reason, on the left-hand side of each horizontal line, except for the first one in the lower left-hand corner, there's a closed circle. The closed circle indicates that the horizontal line does include the jump point. The open circles and closed circles are the real reason I wanted to present this plot to you. It was to clarify that one remaining detail about the transition between horizontal values. We'll generally stick with the original way of presenting the EDF. That about wraps up this video. In the next video, we'll begin to reduce the data down a bit, using the EDF to pull out the quartiles of the data, which includes the median value. From these and the minimax values, we'll construct a box plot. So stay tuned, because I'm already working on video 4.2.